This is an example of working with both series and parallel capacitors to find out the equivalent capacitance. So we're going to be using the two ideas that when we have capacitors in parallel, capacitance adds, the equivalent capacitance for parallel is C1 plus C2 plus however many. But in series, the equivalent capacitance for any capacitors that are in series would be given by this set of equations. This is just an example to show you how this works. And the thing to notice about things that are in parallel is the change in potential. The potential difference for ones that are in parallel are the same, whereas ones that are in series, they have the same charge. Okay? So our goal is just to work a made-up problem so you can see how all this works. So the idea here is that we have a battery, so a 9-volt battery, that's our potential difference there, and a bunch of capacitors. So I'm going to have capacitor 1, and we'll have, let's say, capacitor 2, capacitor 3, and then we'll go ahead and add, to make this a more complicated situation, capacitor 4. Now, with this situation, capacitor 1 isn't in series or parallel with any of the others yet, but we can sort of replace them. We can say, okay, capacitor 4 here is in parallel with the two capacitors, capacitor 2 and 3. And so we're going to go through a program where we're sort of reducing this down, okay? So we're going to say, we're going to go, I guess I'll go, so we're going to reduce this down, and I'm going to say, let's take this to 9 volts still, our capacitor 1, but this time I'm going to replace these two with a capacitor that's equal to capacitor 2, 3. Okay, so I'm going to call it capacitor 2, 3, which is now in parallel with capacitor 4. And so capacitor 2, 3 is the equivalent capacitance of 2 and 3 in series, so I would say it would be equal to 1 over capacitor 2 plus 1 over capacitor 3 to the negative 1. And once we have values, we'll work that out. I'm just giving you the overview, and then we'll go back and put numbers in. Now I can see that capacitors, these set of capacitors are in parallel, and so I can have the situation where I now set this up as 9 volts. I've got now C1, and then I have this combination of the equivalent, that's capacitor 2, 3, 4, where capacitor 2, 3, 4 is just equal to capacitor 2, 3 that we find right up here, plus capacitor 4, because those two are in parallel. Okay, and then finally, I think it won't surprise you to recognize now C1 and this equivalent capacitance here are in series, and so these two are in series now. And so that gets us finally to our equivalent capacitance of the whole system. So C equivalent, which would be 1 over C1 plus 1 over whatever we find for these others, all to the minus 1. And so in this kind of setup, just to at least start with, we often are asked what is the equivalent capacitance of the whole system and how much charge is stored. So that's sort of the question we're going to ask. I realize I dove into it without even talking about the question we're going to ask, but let's say we want to know the total charge stored. And to get to that, we're going to need to know the equivalent capacitance. So let's just pick some numbers here to get this started, just to make this easier. We're going, at least number-wise, we're going to say C1 is 1 microfarad, C2 is 2 microfarads, C3 is 3 microfarads, and you've guessed it, C4 is 4 microfarads. Just so it's easier to keep the numbers straight, this doesn't turn out to be such an easy problem once we start to look at it. But it gives us a way to start. So we're going to start down this path. So we're going to say C2 and C3, this equivalent equivalent capacitance, is going to then be equal to C23 is equal to 1 over 2 microfarads plus 1 over 3 microfarads, all to the minus 1. So I'm going to look for a common denominator, which would be 6. So I'm going to have 3 over 6 micro. We're going to know we get microfarads out by the time we finish, plus 2 over 6 microfarads to the negative 1, which is going to be 5 over 6 microfarads to the negative 1, or if I keep going, this would be 6/5 microfarads. So my equivalent capacitance now is 6/5, which I think is now 1.2. So that is 1.2 microfarads. So notice what happened. I had 2 microfarads and 3 microfarad, and it gets replaced by an equivalent capacitance of 1.2 microfarad. So we've reduced the overall capacitance, which really shouldn't be a surprise, because when they're in a series like this, they have the same charge, so they're not storing overall as much charge. You can almost think of it as two plates that have extra area between them in some sense. So this is 1.2 microfarads. Okay, moving to the next part. This next one is fairly easy. We can say my equivalent capacitance here, this is 4 microfarad, but when I put them together, it just, it's 4. Okay, it just becomes then my 1.2 microfarad plus 4 microfarad. So that gives me 5.2 microfarad for this equivalent capacitor. So this is like, in other words, what we're saying is that we could build the same circuit that we have at the top with a 1 microfarad capacitor in series with a 5.2 microfarad capacitor. So it's the same circuit. Then finally, as we get down to sort of the bottom of this, we can say the equivalent capacitance here is going to be equal to, now we've got, these are in series, so we're following this plan. So this is 1 over 1 microfarad plus 1 over 5.2 microfarad to the negative 1. And when I put that in, this gives me, okay, so 5.2 are 4 plus 1.2. You can also write this if you want to do this in fractions, right? This is 6 over 5 plus 4 microfarads, which if you get a common denominator gives you 6 over 5 plus 20 over 5 all microfarads, so that's 26 over 5 microfarads if you want. And I'm using this here just because we can get the number here. But you can just use your calculator, right? So 1 microfarad, and this becomes 1 over 5 halves, 5.2. So remember, this is 26 over 5 microfarads, is now going to be 5 over 26. Oh, I lost the 6. 26 microfarads. So a common denominator means I got to be 26 times 26 here, or I get 31 over 26. 26 microfarads to the negative 1, or this is 26 over 31 microfarads, which is maybe not the most useful way to look at it. If you plug it into your calculator, you will find right away this gives you, at least when I did it, 0.839 microfarads, or 26 over 31 microfarads. So the equivalent capacitance here is 0.8439 microfarads. So I've got to build this whole circuit with just this capacitance. Okay, great. We still haven't found how much charge is stored, and this is the point at which we can find the charge that's stored, right? Because we can say Q is equal, the charge stored is equal to the capacitance times the voltage difference. Well, now I know the voltage across this equivalent capacitance is 9 volts, so I can say this is 0.839 microfarads times a voltage difference of 9 volts, and now I really do need my calculator. I get 7.55 microcoulombs. I'm just carrying the micro instead of turning it into a 10 to the minus 6 that I have to carry everywhere. So that's the total charge stored, which is sort of the question up at the top. What I'm going to do is show you how to do sort of the rest of the pieces, which might be the Q on each capacitor and the delta V across each capacitor, just so you can see ways to calculate this and also to check it. So to do that, we work our way backwards through the problem. So I've got the total charge now. So I've got Q is equal to 7.55 microcoulombs. And now I'm going to work my way backwards. So I know this charge. I know that the charge is the same on these two capacitors, right? C1 and C2 now both have 7.55 microcoulombs. Charge of 7.55 microcoulombs, because the charge on the charge can't build up. So whatever charge I have, whatever negative charge I have on the right side of plate C1 has to be the same as the positive charge at the top of C2, because there's no place for it to pile up. So they both have a charge of 7.55, which comes from our rules way up here of the charge being the same for capacitors in series. Okay, so orienting back to where we are, here we are. We've got the charge on each capacitor. So now it's pretty easy to again use our Q is equal to CV to find our voltage across each capacitor. And we know that that voltage had better equal 9, right? Because otherwise energy isn't conserved. If I've got 9 volts here across the battery, then that means I have to have 9 volts across both of those two capacitors. So if we plug that in, so if we do that for my C234, as I'm calling it, right? The charge is 7.55 microcoulomb. The capacitance is whatever it was, 5.2 or 26 over 5. If I plug that in, I get, so in here I put in a 5.2 microfarads, and so that gives me a voltage that is 7.55 microcoulombs over 5.2 microfarads. The micros conveniently cancel each other out, and I get something around, I get 1.45 volts is my calculation here. If I do the same thing, of course, for the first one, that's pretty easy, right? So if I'm looking at this, then I can say Q is equal to CV, or that gives me then that my voltage is equal to 7.55 microcoulombs over 1 microfarad. Okay, this is math I can do without a calculator. That becomes 7.55 volts. And now we can check. 7.55 plus 1.45, that does in fact equal the 9 volts we expected. So you can see how we can check our answers as we go along. So we can continue working backwards with the information that we have. So we now know that we have 7.55 volts across here. That's the voltage difference across C1. We know we have a charge of 7.55 microcoulombs. Now we know that across both of these parallel resistors, we know then that C23 and C4 together store this charge. Now they've split up the charge because they don't have the same charge, but altogether they're going to store a total charge, a Q, across all of them of this 7.55 microcoulombs. So we found our equivalent capacitance, so we don't need this anymore. And we're going to just keep working our way through this. So we know also that the voltage, this voltage difference, delta V, is equal to 1.45 volts. That's across the network, and so that's the same voltage, okay? When they're in parallel, they'd have the same voltage. So this is a voltage difference of 1.45 volts here, because from here to here has to be the same voltage, which means that's the same voltage over the C23 as is the same voltage over C4. Okay, now we can just again we use it over and over again, this Q is equal to CV. So for 4, Q4, C4, and the voltage across 4, we can put in all these numbers. So we get charge on 4 is equal to 4 microcoulombs times 1.45 volts. And when I multiply that out, I get some number. I get 5.8 microcoulombs, so for Q4. So we're expecting, since the total charge on these is 7.55, that if we subtract those two, we should get the charge on 2,3, but we'll go ahead and work that out. So the charge on 2,3 is equal to its capacitance times its voltage. So that means charge on 2,3 is equal to 1.2 microfarad times 1.45 volts. And when we put that in the calculator, I get 1.74 microcoulombs. And so when I add those together, when I add this to this 5.8, I get 7.54. So I've got some rounding, but basically I've got the right answer here. Everything is consistent. Okay, so we're almost done. You can continue this. You don't have to, right? Unless the problem that you're working with asks you. But now we've got the charge on this capacitor, Q4. So we've got 5.8 microcoulombs. We know the voltage, delta V, is equal to 1.45. That's for 4. Q4. We already had Q1 and V1. That's Q1 and that's a V1. Right? We already had that. So then it's just a matter of finding out what's going on for 2,3. And 2,3 stores 1.74 microcoulombs. So they each have Q2 equals 1.74 microcoulombs. That's coming from all the way down here that I just marked. Okay, this Q23 is traveling up here. And so my, and the charge on 3 is the same, 1.74 microcoulombs. So then we can find the voltage on each of those, right? So we can use, again, Q2 equals C2 V2, right? And Q2 we know is 1.74 microcoulombs. C2 was 2 farads. And so now we can find the voltage for 2. And the voltage for 2 is equal to 0.87 volts. If we do the same thing for 3, Q3 equals C3 V3. We still have 1.74 microcoulombs. This time we have 3 microfarads because that was the capacitance of the third capacitor. V3, that gives us a V3. It's going to be a smaller number, right? And it's going to be 0.58 volts. And if we add these two together, I get back my 1 point, and this time with the rounding I get 1.75. Okay, so I get the voltage, I get the charge that I expected, this 1 point, I get the voltage that I expected of 1.45. So sorry, yes, I add these two together, that gives me 1.45, which is the voltage I expected. So now I've got this thing completely parameterized. Now, would you actually build a circuit like this? Probably not, but sometimes you build things because of the capacitors that you have, and you want a particular value, or the limits on the capacitors. Some capacitors can't have a full 9 volts across them, or 100 or 1,000 volts across them. And so you end up playing these kinds of games with these networks. The point of this is that you can replace a capacitor group by either saying it's parallel, oops, zoomed in a little too far, by saying it's either parallel or it's series. And we just used Q is equal to CV over and over again, along with our equivalent capacitance and our equivalent resistance, and what was the same, right? So that's really your key. Your key to all of this is what's sitting right here.